Right, okay. Okay, students, then this is your third day of your chemistry O-level seminar, and when you are getting this recording, you will be in the middle of your O-level exams. So I hope you are doing well. And yeah, so we were able to have a O-level seminar for science, and we were able to cover 3 days of physics, which was done by Janindri Ananda sir, and I myself did 2 days of the seminar. Actually, we also had 3 days, which are extra day, and today I am covering the day 3 of your O-level chemistry seminar, but upon request we thought of giving this as a recording. Now you are watching that recording, right? And today we are trying to cover the most important parts of your mixtures lesson, because when I ask you, this lesson was chosen upon your request. We put a Google form, and about more than 100 students submitted, and out of that roughly around 40 to 50 students requested us to finish this lesson as they gave that the highest priority. Right. Then today we will be covering that part, right? And if you have questions, you can put a question on the YouTube chat after this has been uploaded to YouTube. Then I'll answer that personally. Hari? Right. Then before starting, you need to know that once I went through the mixtures unit, what I realized was a certain part will be mostly asked for your A levels. Apart from that, everything is just theory. You can go through it shape again, and no need to bother about that unit. So I won't be and don't expect me to cover the entire unit, go from the very beginning to the end within a single session. I can do that personally, but that will take around 4 to 5 hours of recording. Then it's not that effective. You won't go through that recording. So what I'm going to do is I'll show you the basic structure of the unit, and then I'll show you what part I am going to discuss here, and why that part is being discussed. So basically that's the part which is most commonly asked for your exam, right? So today we are not trying to cover or revise the entire unit, which is not what we did in day 1 and day 2. Day 1 and day 2 we tried to finish the entire units, because those two had a huge proportion of marks, right? A considerable proportion of marks. But when it comes to here, a specific part has been asked that contains a significant amount of marks, but apart from that everything else doesn't have a high value, right, relatively. So going through the unit of mixtures, right? Talking about mixtures, the unit, I can divide this unit to several parts, right? So the first part is just basic theory. What are mixtures? Types of mixtures, more polarity, non-polarity. Those concepts have been discussed, and how to determine whether one substance is what substance can be dissolved in as other substance, or whether the two substances are immiscible. එහෙම කතන්දර ටිකක් තියෙන. That's the basic theory. And then we have concepts of mole, how to calculate the number of moles, what is molar fraction, what is concentration. All of those concepts were discussed under the mole part, so no point discussing it again. We discussed those concepts in a higher depth using A-level tips as well, which make understanding and doing calculations easier, so no need to do it again anyway, right? And then we have these extraction methods. How to extract a given solution or given substance using another from a solution, right? So there are few methods, evaporization, and then various methods. I think there were around five methods given. So I won't again go through those, because those are just theory. You need to know the methods and just a brief explanation on what those consists. Right. From there onwards, we have a few parts which are kind of a more practical knowledge rather than just understanding the theory. I will be covering those parts. So basically we will be covering the simple distillation, and then the fractional distillation, and then the steam distillation. I'll explain those, because those things are the ones which have been mostly asked. There's a reason for that, because those things are the ones which are related with your A-level exams. Right now, O-level is actually a preparation for A-levels, right? So in A-levels, these things are given in chemistry, under chemistry, which are important, which contains important theory and practical knowledge. So I'll be covering those parts, and then afterwards I'll cover that chromatography part. Here I'll explain what that is, and that's actually a kind of technique which we use to separate components from the solution. I'll explain that part, the chromatography part. And then afterwards, finally we have extraction of salt and essential oils. Extraction of salt and essential oils, which are actually practical applications in real life, as in real industries. So for essential oils, I will be explaining that under essential oils are being extracted actually using the steam distillation, which I am going to teach here. So I'll combine those together. And when it comes to salt extraction, on your syllabus they don't expect a lot of practical knowledge or a lot of theoretical knowledge, just studying. They have simply given the conditions which you require to extract salt, and then the stages of salt extraction. Apart from that, they haven't given a lot, so I won't be focusing on this part. It's just basically studying. So I will be discussing the distillation part, chromatography part, and I'll be combining essential oils with the distillation part. So that's the part which you need a significant amount of understanding and mostly be in questions. So I thought of discussing those parts, right? But again, if you have issues regarding any of these parts, so this we covered anyway. If you have issues regarding any of these parts, you can put it on the chat, or else students who are on our WhatsApp group can directly text me on our WhatsApp number. So me or someone from our crew will respond you with the perfect explanation, right? If that's clear, then we are good to start. Then let's start. Hurry, right? Okay, is everything fine? Is everything okay? Right. Then put a small topic and write. Before that, give me a minute. Right, okay. Right. And also another thing that you need to note now, since you might not have been used to watching a recording. Recording means there are two types of recording. One recording is that I am simply recording the live class, and then you will get a copy of the live class which is recorded, right? But this recording is special. This recording is done in an environment where no students are participating live. This is just recording. I am just looking at a screen, looking at the camera and the laptop, and working with the smartboard and giving you a recording, right? In that case, I won't be giving a lot of time to write the notes, or else if I ask you to do any calculation, or if I ask you to answer any question, I won't be giving you any time, simply because you can't pause, because no students are joining live. Therefore the recording length will be slightly shorter. If we did 3-hour sessions, I can finish this at around 1.5 hours roughly. I understand that as well. Otherwise you will think, why isn't he given time to write or anything? So that's why I explained. Alright. Okay, where is it? Yeah. Okay, put the topic simple distillation. Simple distillation. Even here you need not to write a complete note. You can just go through the video quickly and then get the idea, because you will be watching this video at the very last moment. Anyway, steam distillation. Under steam distillation, now for all three distillations, steam distillation, fractional distillation, and steam distillation, they have simple distillation, fractional distillation, and steam distillation. For all of these three, they have given you rough sketches. So mostly they won't expect you to draw a sketch, but mostly they will expect you to, if they give the sketch, that you know all the components. If they ask you to name those components, and if they ask why these components, why these instruments have been used, and what are their objectives, what do they fulfill, Hari, and you need to be able to answer those, right? So I'll just draw a small sketch of the steam distillation, and then I'll explain. So you need to know that in a practical environment, the sketches can differ, right? There can be different sketches for the same experiment, but I'll just draw what is given on your resource book, Hari. Actually, the textbook. Here we can connect the Liebig condenser. I'll explain how a Liebig condenser works. And then this Liebig condenser can be connected to a small container. And this is, yeah. And generally, the water container or the sample in this container can be clamped using a clamp and a ring stand. This is known as a ring stand or a supporter, doesn't matter. Right. And you have the thermometer. Something. This is just a rough sketch. Alright, so if I explain this, the most important part is that you need to understand the mechanism of a beaker. The Liebig condenser. And before that, you need to understand for what we are using the simple distillation. So the basic idea of a simple distillation process is that if you have a solution which contains one volatile component and an unvolatile component, then to separate those we can use this the simple distillation, right? So the idea of volatility is now how easy you can vaporize a solution. Now there are no non-volatile components in real, but we normally in day-to-day life we call it a non-volatile compound if the volatility is very low, or else in other words if the boiling point is very high, right? In practical scenarios it's difficult to achieve that boiling point, therefore we commonly name it as a non-volatile component. Volatile නැති ඒවා නෑ, but in general we can say it's a non-volatile component if it has a very high boiling point, right? So for an example, they have given you a mixture with sodium chloride in water. Now if you dissolve sodium chloride in water, now if you want to separate those two, you can use this mechanism, something like that, right? Shall I check whether that's the exact example, or they might have given some more examples as well. Let's see. Yeah. What do we have? Yeah, not even sodium chloride, any salt. Now they have given an example, well water. Well water. Now if you take a sample of well water, it contains various salts, not only sodium chloride, any salt, magnesium chloride, calcium carbonate. There can be several salts. So if you want to, generally an inorganic salt has a very high boiling point. It's difficult to boil it, so therefore those are considered as non-volatile components. Now if you dissolve those in water, water generally is considered as a slightly volatile component compared with the boiling points, right? Now the boiling point of water is 100. The boiling point of inorganic salt can be 1000, 1500 even can be. Therefore the volatility is relative. Then the volatility of water is higher. The volatility of the inorganic component or the salt, sodium chloride let's say, is higher. Is that clear? Then for such a solution you can simply distillate those using the simple distillation. What happens is, let's assume that we have sodium chloride and we have water, right? Let's assume that we have these two. Then what can happen is you just simply need to give heat, and that heat should make the temperature reach 100 Celsius, because that's the boiling point of water. It should reach 100 Celsius. Then once it reaches 100 Celsius, what happens is that water will evaporate, but the sodium chloride won't, because that's not enough to evaporate the sodium chloride part, right? Generally it won't be 100. Now there are several concepts. Now if you mix two substances together, then the boiling point of the mixture can be different from the boiling point of the pure components. Now let's say the sodium chloride boiling point is 1000 Celsius, I don't know, and water let's say it's 100, then the boiling point of the mixture can be something else. But for the moment we just ignore that fact and we just think that the boiling point of water is 100 and this is 1000. There's no significant impact of the mixture, right? In this case there's actually no significant impact. Then what happens is, once you boil it, water will boil at 100 but sodium chloride will remain in the container. And then what happens is the water will boil and it will be water vapor, right? Jalavaspa, it will be water vapor, H2O gas. Then that gas will enter the Liebig condenser. Right? That gas will enter the Liebig condenser and sodium chloride will be separated. Now the Liebig condenser does is actually condense. Liebig condenser will actually, it should be this, yeah. It actually condenses a gas to a liquid. Now how does that happen? It happens like this. This tube, this is a thin tube which is covered using a water jacket. That's known as a water jacket. It looks like this. Right? There's a small opening here and there's a small opening like this. This is how it looks like. So this is a water jacket. Now it's just now if you let's say this is the thin tube, then it is covered by a small covering. Now assume that you build a tunnel inside the sea. Now can water enter the tunnel? No, the water can't enter the tunnel, but it is the entire tunnel has been surrounded by sea, something like this. Now this is the tunnel, this is the sea, which is entirely surrounded by another covering. Now what happens is we enter water from here, and the water will be emitted from here. So what happens is it's a continuous process through the entire time period where the water vapor flows. Now water vapor is flowing from here to here. Now water vapor is flowing like this. There's a covering which contains water, and that water is flowing continuously. It's not just water here staying still. The water will be moving continuously. Now the speciality of water is water has a very high very high specific heat capacity. The idea of having a very high specific heat capacity is water can absorb a lot of heat, right? That's why you normally are advised to drink water, not only for that, but when you especially in a hot environment, you need to bathe well, wash well, simply to absorb the heat, right? So water can absorb the heat a lot. Then what happens is, no matter what gas, it's not only for water vapor, right? There can be many gases traveling through this tube. But what happens is, for that gas, it contains a lot of heat. That's why it's a gas. Now, if you want to make a gas, you need to heat it a lot, right? Then only it becomes a gas. Therefore, this gas will have a lot of heat energy. That energy will be entirely absorbed by the water which is flowing. So if you enter cold water from here, hot water will be emitted. That energy will be entirely absorbed, making this gas a liquid, and that liquid will be poured here. So you can collect the water from here. That's how it happens, right? That's how it generally happens. The basic idea, but it's a little bit different than that, right? Give me a minute. Yeah, that's it. Yeah. So what I was saying, sorry, the water will be vaporized and it will be condensed, and the salts will be remaining in the container, right? This is for the simple distillation, but it's little bit different, which I was saying, when it comes to a component which has more than one volatile component, or else components which have equally similar or nearby boiling points. Then you will have to use the fractional distillation method. So for now, it's very easy. You need to understand how a Levy condenser works, and for what sort of solutions we can use the simple distillation, and then how does that process happen. Just a random idea, and you need to be able to name the Levy condenser, and then thermometer. What's the use of thermometer? Because you need to know, you need to be able to control the temperature. If you give a higher temperature, then both might vaporize. You need to control the temperature. So for those cases, you use a thermometer. Right? That's it for simple distillation, which is the most simple part, right? That's easy. Normally they won't ask questions from this because this is easy. They can ask a very little amount. But generally they will ask you the fractional distillation part and the steam distillation part. So we'll continue. Right, then you have the fractional distillation part. Fractional distillation. What's fractional distillation? Fractional distillation is the process that we use to separate few volatile components which are in a single solution. The most general example, which is also given in your resource book, is separation of components from crude oil. Crude oil can borotil. Now you extract crude oil from the earth, then that has a lot of components: gasoline, which is petrol; diesel; naphtha, which is another type of a fuel you might have heard of. And then you have a various amount of components, around 10. Sometimes it can be more than 10. Now on your resource book they have given few. They have given petrol, chemicals, jet fuel, which is known as rocket fuel also. And then you have diesel, bitumen, which is also known as asphalt. Asphalt carpet not all roads that's been used. For carpet roads you use the bitumen. Goda components in crude oil, right? So those components have boiling points which are not that different. Now for the first example, the boiling point of water and sodium chloride was very different, but for this case it's not. Then you can't just use simple distillation because you have a lot of components and the boiling points are close by relatively. Therefore you need to use the fractional distillation. Now let's learn how that fractional distillation happens, right? Let's check whether they have given a practical for that. No, they haven't. Right? They haven't given a practical for fractional distillation. They haven't drawn a sketch. They have just shown you the fractional column or the fractional tower, which is normally used as fractional column in A-levels. Here they have given it as fractional tower, fractionating tower actually, and they have showed you how that happens. So I'll just give you the basic idea on what happens. So what happens is, as you can see, I'll just try to explain now. I'm talking about the 60th page of your textbook. Now they won't ask you to draw these things. You just need to have the general idea on what's happening. Now if you closely observe the tower, now these things can be asked. Now if this is the tower, look at the temperature closely. The boiling point of the components which are being taken on the top is around 25 Celsius, which is a low value, right? And on the bottom it is around 250, 300 Celsius. So you need to know that the temperatures of the boiling points from each component to component will be lower on the top and higher on the bottom, right? So the components which have less volatility will be extracted on the bottom, and the high volatility will be extracted at the top. Now you need not to worry about how those are being extracted, because in even A levels we don't analyze such a solution having a lot of components. Even in A levels we analyze solutions which are having roughly 2 or 3 solutions. No need to bother about this. You just need to know these two. And other than that, let's say what is more important than that. Yeah, and you also need to know a general idea on how this happens, not the practical idea. Now, it's actually difficult to explain what happens here. Even in A levels, they don't expect. But you need to understand, if you have a component, if you have a, like I'm drawing a simple structure of this as a small setup, right? As a small sketch. Now assume that you have two substances which is X and Y, and the boiling point of X is 40 and the boiling point of X is Y is 80. Let's say this example is given, so they expect you to explain the fractional distillation, the simpler version. This is also what we are doing in A levels. We don't go beyond that. If you have like 3 components, it can be a little bit complicated, right? So here we have like 10, then it's different. You have to create a lot of levels. So you need not to explain this theoretically, but have a general idea on what's on top and what's on the bottom. Explaining a very simpler structure, what happens is, now if you have two components which mix well and which are similarly volatile, now in a scale of like 0 to 1000 Celsius or 2000 Celsius, 40 and 80 is like a very small difference, right? Then what happens is the volatilities of these two are very close, right? Now if you heat this, the boiling point of this mixture will be something higher than 40. Normally it will be something higher than 40, less than 80. Let's say 50. At 50, both will vaporize in proportions. Now you might be wondering, how can Y vaporize, because the boiling point is 80. Now once you mix these two, that's what I mentioned previously, once you mix these two, there's no X or Y, it's just a solution. These two act as a one individual solution, right? Therefore you can't say the boiling point of Y is 80, how can it boil at 50? No, the boiling point of the mixture is 50. Then at 50 both will vaporize, but they can remember their volatility slightly. Therefore the one with the higher volatility will vaporize a lot, this will vaporize a little bit. So what happens is, let's say for an example, you had 5 moles of this and 5 moles of this. I'm just trying to explain this because that's not properly explained now. Students might have doubts. Then after vaporization, let's say 4 moles of Y vaporizers leaving 1, but only 2 moles of X vaporizers leaving 3. So that's the basic idea. So you give 50, this is more volatile, so this vaporizes, sorry, this is, so the other way, no? Should be the other way. This should be 4 and this should be 1. And this should be 3 and this should be 2. This is less volatile, having higher boiling point, which means it doesn't like to vaporize. So that's what happens. Then, as you can observe, here even though the number of moles were similar, here the number of moles are not similar, right? Then what happens? As you can see, since the more volatile component has vaporized, now the volatility of this solution altogether has increased or decreased? Decreased. Why? The person, the substance who likes to vaporize more has been already vaporized a lot. Now considering this sample, what has happened is the volatility of this solution has been decreased, which means you need to give a higher temperature if you want to boil this part. Is it clear? If you want to boil this part, you need to give a higher temperature. That's the idea. So you need to be able to explain those things. Now if you check your textbook, I'm always trying to go with your textbook because that's the important part. Hari? Yeah. So they have clearly mentioned these. They have taken two examples, two components as A and B, and given two boiling points, and they have explained this process. Now they can ask, now to boil this solution, the required temperature was 50. After boiling it for few minutes, the required temperature to boil the remaining solution was 70. Explain why. Now you need to be able to explain why. Because the more volatile substance has been vaporized a lot. Now comparing this solution with this, the volatility of this entire solution has been decreased. Therefore, you need to give a higher boiling point. You need to give a higher temperature, right? So those things you need to be explained. That's the basic concept of fractional distillation. But apart from that, when you have more than two components, you need to use a column. You can't just use it in a small container. Then you need to have several levels which you can see. And comparing those levels, the boiling points of more volatile substances will be collected here. Less volatile substances will be collected here. That's more than enough to explain your questions, right? I gave you some sort of a guidance using A-level theory as well, because most of students might not even know how to explain this theory. That's the most important part. Apart from this, remember these two, right? So that's for fractional distillation, and remember that we use fractional distillation to distillate crude oil. And remember few components of those: gasoline, petrol, diesel, rocket fuel or jet fuel, and then asphalt or bitumen. Remember few of those. That's enough, right? So that will do regarding fractional distillation. Hari, right? Okay. Then let's continue. So you can write a small sketch or small note, and that's it. Then the third one. Third one is what? Third one is the final part. The final part will be actually steam distillation. Steam distillation. Now this is completely different from what we have learned up to now. Even though you learn these three in a same topic, that might be the issue as well. Some students aren't aware that even though this is a distillation, we learn these three in the same topic, that the concept of steam distillation is entirely different from what we have learned. Now actually, the concept of simple distillation and fractional distillation are more like the same. Only thing is that the solution gets a little bit more complicated to differentiate or to separate. Therefore, we need to use a more organized method, a more organized theory comes through. But when it comes to steam distillation, the theory is completely different. What happens is completely different. Now, up to now, both the components, right? Both the components were actually mixing well, right? No matter what the boiling points were. Now, if we take water and salt, if you add some let's say some mass of salt to water, it will easily dissolve and it will easily mix. No need to force, right? But if you add also if you add petrol, diesel, gasoline, and crude oil, everything is not crude oil, bitumen and everything to a container, everything will be easily mixed. So those were natural mixers, right? Natural mixtures. We didn't force them. But here, steam distillation is a concept where we use for two components which don't prefer to mix, or else immiscible two components, right? Now you might be wondering, why are we bothered about immiscible components? Now if they are now, from the previous two concepts were to actually separate two components, right? We put the effort to separate two components which like to mix together. But now we are talking about a scenario where they don't even want to mix, but we are mixing them and then trying to separate it. Why? What's the matter? We can just leave those as it is. Ne? The matter is that you need to learn a theory to explain this. Now, if you have, let's say, I'll take the example which is given on your resource book as well, the textbook. Now, if you take water, what's the boiling point of water under our atmosphere, which is 100 Celsius? Normally, this steam distillation is used in various industries. The common industry which is given for you is the essential oil extraction. Therefore, I'll try to combine this that part with this as well. Then you will get a clear idea. Under essential oils, what are essential oils? Those are essential oils, right? We will be talking about cinnamon oil extraction from cinnamon leaves. Cinnamon oil from what? Cinnamon leaves. Cinnamon leaves, right? Now, if you want to extract cinnamon oil from cinnamon leaves, what you can do is, the general idea is, you can take a cinnamon leaf and then boil it until a point where the oil or the liquid which is inside the leaf evaporates, and then you can condense it back, right? But the issue is the boiling point of the oil which is inside the cinnamon leaf is around 160 Celsius. But the leaf itself can't bear that temperature. Now the oil which is inside can bear that temperature, which will then evaporate, but the leaf cannot bear that temperature. What will happen is if you give that much of a temperature, the leaf will disrupt, or the leaf will let's say decompose, destroying all the oil or the chemicals which is inside the leaf. So we can't afford that. That's not practically doable. Is it clear? Then for those cases, we are using a very interesting theory. What we are doing is we are making a pulp, or we are making a mixture of these cinnamon leaves and adding it with water. But the issue is water doesn't want to mix with cinnamon oil, or sorry, the cinnamon leaf pulp. Those two do not want to mix, which makes the solution, which makes the two components immiscible. Now you need to know these terms. If two components don't want to mix freely, that's known as immiscible. Now the solution is immiscible. The two liquids are immiscible, water and that the pulp which we made out of this cinnamon leaves. Is it clear? Now what happens when you mix is they don't mix, but there are ways which we can forcefully mix. You can stir it, you can heat it, or else there are more advanced methods which we can use to forcefully mix these two liquids. Once you forcefully mix these two liquids, a strange thing happens. What happens is, now if the boiling point of this is 160 and if the boiling point of this is 100, if we forcefully mix these two, this theory will be only applied to two liquids which do not want to mix but forcefully mixed, right? If two want to easily mix or naturally mix, in the examples which we did previously, this theory can't be applied, right? Only for these cases. බලෙන් mix කරොත් එහෙම the boiling point of the solution will be always less than both of these, which means the boiling point should be less than 100. Less than 100. Is it clear? That's the theory. That's what we are using here. So what happens is when you mix these two and forcefully mix these two, actually the boiling point of the solution will be less than 100. So you can easily provide a temperature. Let's say the boiling point was 95. You can provide a temperature of 95 and extract the oil without damaging the leaf, because the leaf can actually bear a temperature at a 95 Celsius temperature. Is that clear? That's what happening here. කොළයට දැන් දරා ගන්න පුළුවන්. කොළයට දැන් ඔරොත්තු දෙනවා. Therefore you can use the 95 Celsius thing. That's actually a trick which we use to separate sorry, what did I do? Right. To separate cinnamon oil from cinnamon leaves. That's what we are doing here. So they have given a small sketch for that as well. From there onwards, after explaining the theory, the sketch is similar to the simple distillation, nothing else. So if you go through the sketch which is given on your 61st page, right, 61st page of your textbook, I'll just explain the sketch. Okay, as you can see, there's the main container which contains cinnamon leaves and water. Now you know why we mix those two, and you can see from on the left hand side you have a water container which is heating. So why do we use water with heating? Instead of just giving the temperature to the container, instead of just giving temperature, we use steam as the component to give energy. So we heat water and then steam will be given. That steam will be used to increase the temperature of this container. Now if you check the diagram, you can see a container like this which contains water and cinnamon leaves. Instead of just giving temperature here, what we do is we heat water. We heat water and then that will give us steam. That steam is directed here. You can see that. Then this will be heated and the solution will contain both cinnamon oil, the vapor form of cinnamon oil because it is being vaporized, cinnamon vapor, and then you have water vapor. So those two will be evaporated. Here you have cinnamon vapor and then you have water vapor, and both will be gone through the Liebig condenser, eventually condensing both. Now you might be worrying, now after the condensation, won't those two mix? No, why not? Because eventually we know that those two did not want to mix. So even though the vapor contains both of these, after going through the Liebig condenser, the same Liebig condenser which we learned, those two will be condensed and give you the liquid. After making the liquid, again those two will separate into layers because those two don't want to mix. These two are immiscible liquids, right? So you know that the cinnamon oil is more dense than water, so cinnamon oil will be here and water will be right. So that's the idea of steam distillation. Is it clear? The most important part is why it is important to mix these two. What's the importance? Why do we bother about forcefully mixing two components which don't want to mix together? Simply to decrease the boiling point. When the boiling point decreases, you can save the cinnamon oils without decomposing. So that's the basic idea of steam distillation. Now I combine the concept of steam distillation with cinnamon oil extraction, but you can use it for many more substances, but the same theory will be applied. So you need to find a solution which two liquids which doesn't want to dissolve together, which are immiscible. Then you can continue from there onwards the same theory, right? I hope that's clear. So I explain a very important theory, very valuable theory which gives you a lot of marks in a very small amount of time. So those three are the main things which I was expecting you to teach, and I'll continue with the chromatography part, and then that will be it for this recording. Right? මේ ටිකේ මොන හරි ප්‍රශ්න තියෙනවා නම් always put it on the chat. හරි? Chat එකට දාන්න. You can put it as comment on the YouTube. Then I'll answer those. හරි? Right. How long is the video? Around 35 minutes. Okay. I think within 1 hour we'll be able to finish the recording. That's simply because I'm not giving you time to write or think or ask questions. If that happened, the recording would have been 2.5 hours. Okay, anyway, doesn't matter. Right? Okay. Shall we continue? I hope everything is okay. Chromatography. The final part is chromatography. Right, I'm going to explain. I'm hoping to explain this part. Sorry, the chromatography part. Again, that's not that difficult. You just need to know what happens here. If you know, if they ask questions, you can easily answer. So I'll just start using the concept. No, not the concept, the experiment. I'll explain what happens in the experiment, right? So, or else, the basic idea of chromatography is there are various methods of chromatography, but we are using what we are using is known as the paper chromatography. කටදාසි වර්ණ ලේඛ ශිල්ප කියලා තමයි මේකට කියන්නේ. The idea of paper chromatography, or the idea of chromatography is, now if you use a piece of paper, doesn't matter what paper. Now on the paper, the example also they have said you can use filter papers, chromatography papers, A4 papers, or basically doesn't matter what sort of papers, right? If you use a strip of paper and if you place a dot of any substance or a mixture which contains various components will make various components will make attractions with the paper which have different magnitudes. So let's say inside this solution you have a component named A, component named B, and a component named C. This is the concept which they will ask you. Now if A makes a strong, now A can make a strong attraction with the paper. The A molecules can make a strong attraction with whatever the chemicals in the paper. Paper එකේ හදලා තියෙන chemicals වලින්නේ. B can also make an attraction, C can also make an attraction. If the attraction which these compounds make with the paper is higher, then it won't travel a lot. Now what happens is, if you keep the paper like this, the strip like this with a dot like here, the components will start to travel upwards like this. It will absorb and try to go up. But if the attractions are powerful, then the paper itself will stop these drops or these components traveling because the attraction is higher and it will pull. Again, why? Then attract a line, something like that. So you just need to know if a substance can travel a lot, then the attraction is weak. If a substance can't travel a lot, then the attraction is less. That's the important theory point you need to know. So scientists have done various experiments and they know which substance using which paper will travel how long. Now if you use a A4 paper, scientists know how far can, let's say, a drop of ethanol can go, how far a drop of methanol can go. Now if you after they find that, if you use the same paper and if you use the same solution which contains ethanol and methanol, looking at the distances it travels, you can say whether it's ethanol or methanol. That's the concept which we are using. We know if we have ethanol how much it travels. That has been determined by previous experiments done by scientists. Then if it travels that much, we know, okay, this is ethanol. If it travels this much, you know, okay, this is methanol, something like that. Using that concept, you can derive or you can explain what solutions are inside this container or this mixture. That's what happened. That's a very simple experiment type. Right. So they have done a small experiment using this concept, as you can see in the 63rd page, right, inside the. So now once I explain, you will understand that these concepts are really easy, right? You just lacked the basic idea or a basic explanation on what's happening here. It's right. So you can see there's a small experiment. You have used a tube. They have used a tube and it has been sealed, which you can see. And then they have used a small hook, and then this paper strip is hanging. That's important that the paper strip cannot be touching these walls of the beaker. Sorry, the beaker, not the beaker, the boiling tube. And then there's an important thing which can be questioned. They are using a solvent. Like this, right? And then you can see there's a chlorophyll drop which is given here. Now this experiment is actually done to identify what components are included in chlorophyll. Therefore, placing a chlorophyll drop makes sense. So let's say we have 3 components in chlorophyll, then those 3 will travel 3 different distances, and then you can say, okay, these 3 what were the components. That's easy as that. But there are a few things which might not make sense at once. The first thing is, now if you go through this, they are saying method, crush a few leaves, and okay, so they have explained how to form a chlorophyll drop. So they are asking us to collect few leaves, spinach leaves, and then cotton again, using the mortar and the pestle, and then make a solution and then get a drop of that, which is okay, that's fine. That part is okay. But what might not make sense is that they are saying cut the strip, everything is fine. The fourth point, they are saying add a solvent such as acetone, kerosene, petrol to the boiling tube and stop it. Leave it to saturate. Connect a hook. Alright. Now why might that be important? Now they are telling us to add gasoline. Are they? Yeah, something acetone, kerosene, petrol. Yeah, gasoline, petrol. Some volatile substance like that, which has nothing to do with the experiment. We are experimenting chlorophyll. Right? Why is it important? Any ideas? The idea is actually, now this chlorophyll, the drop can actually vaporize. If it vaporizes without traveling upwards, everything will be useless. The experiment will be useless. It won't travel. Instead it will vaporize. So to prevent the vaporization, what we do is we saturate the entire boiling tube. What's saturation? Saturation means a saturated vapor phase. Now this boiling tube will be a saturated vapor phase. Which means more liquid cannot vaporize because the tube is entirely filled with the maximum amount of vapor which it can contain. How can we make sure that it is always saturated? By having a solvent which is highly volatile. Now if you observe the components which are acetone, kerosene and petrol, which are highly volatile, vaporize, right? So if you fill a little bit of kerosene or petrol, then it will volatile and contain all the empty spaces by vaporizing itself. Then there's no room for any other vapor, which means this won't vaporize. To prevent that, we use those, right? So you need to be able to explain those concepts which can be important. Right? That's the importance of that. Have they explained that? No. Actually not. So that explanation is not on your textbook. So they might not ask, but sometimes they might try to ask few questions to check whether you have understood what's happening here, right? So that's actually chromatography. Not that difficult, but you need to understand few concepts. Now, in my opinion, normally your this mixture part will be given as a subsection of the sixth question, if I'm not mistaken. So there will be three parts. It can be 6 or 7. I can actually remember. It can be, so generally it will be three parts: A, B, C, and A, B, and C, right? A, B, and C. And in my opinion, they will ask about acids, bases, and salts in one part, and then that hydrocarbon in another part, and then this can be combined. Now, I haven't gone through the past papers, the entire past paper, but I will go through the entire past paper for few years, which I actually went, but I can't now remember. I will go through that entirely, and then I'll give you a small idea on guessings, right? Guessings means I'll predict that these questions can be or will be asked in your exam paper, but I'll send it to the group 1 day or 2 days before your exam. So basically, guessings are just to make you more confident, to make you more efficient, to let you know that these things can be asked using my experiment and experience, and say that it's better if you can go through these. But never rely on my guessings, because if you can guess the entire paper, then no point teaching you 2 years, right? No point having these seminars. I can just say, okay, these things will be asked, study those and go to the exam. That's not the point. I just want you to know that these things can be asked. The probability is higher, but those might not even, right? Don't rely. That's not the point. But I'll send you a short voice note saying, okay, I guess that these things can be asked. Right. Then I think that's it for this lesson. So what I want you to do to get the most of this lesson, I always, before finish a seminar, explain what I want you to do to get the most. Uh, have a small note, because I predict that this is the most important part. Go through that salt extraction as well. We covered this. Go through this and check what theory you are missing. And under essential oils also, they have a few more theories, not any practical ideas, not any chemistry related stuff, but they have given that this tree can be used to extract this flower can be used to extract this, just some studying stuff. If it's possible, go through those as well. And then this part we covered, you need to be okay with it. If you are not, go through the mole seminar, which is important for many lessons. Go through that definitely. And then the basic stuff is just studying types of mixtures, everything you need to know. A small MCQ here and there can be asked. Don't give up free marks, which you can carry from home. And under extraction, nothing much. Under extraction, just there are 5 methods. Just study 2 or 3 methods and names of methods, and you need to be able to explain it in your own words what happens. No need to study the entire paragraph which is given in your textbook. You just need to be able to say, if I ask, okay, vaporization, explain how you can separate two components in one solution using vaporization, right? Something like that. If you want to just show you a small example, let's say that now I'm teaching you how to write an answer. Right? Yeah. So let's say you know the method of separation or extraction as filtration. You know the method filtration. Now they ask, write a method and explain it. Filtration. So you need to explain what filtration is basically. So you can use filtration to separate a component which is suspended in a liquid. Then once you filter it, the liquid will flow out, and the suspended material or the component substance will be remaining. Something like that. So then the suspended amount will be left, and the filtrate can be taken as the liquid. A small idea. Now if they ask to explain vaporization, you need to be able to know for what types of solutions do we use vaporization and how to do it. If they ask about crystallization, what's crystallization, how to use it, where are we using it, what's recrystallization, how to use it, where are we using, something like that. Very simple. And for some, I think they have given small examples as well. For an example, solvent extraction, they have given a small example. So you need to be able to know those. So nothing to explain. It's just theory, which you can go through very quickly. I know I personally figured out that the part which I did was the most important part. So for a student who has no idea on which part is actually important, first go through what I did and then try to complete the other sections of your mixtures unit. Right, then that's it for today's work, and so stay with us. I'll send the voice note as well, and from Janidu sir's side also, he might do a few other things in between your examination days as well. We'll see. So I think that we were able to do a significant amount of work in a very short period, right? With you students, I haven't seen any students personally. I don't know anyone. It's just an online seminar, right? And I am satisfied from my side. So I hope you got the maximum, and yeah, and you will do well in your O-level exams as well. So up to now, you might have made few mistakes and you might be regretting those, but keep those aside. Continue, do your best, right? Then good luck again. Yeah, let's meet in the future as well. Right, for now, that's it. Hari, if you have issues again, I repeat, put it on the chat. Hari,